Greetings from the Department of ECE, SJBIT. We will be discussing about Module 1. In the Module 1, in the first part, we have discussed about the addressing modes, assembly language notation, assembly language sequencing, instruction sequencing, memory, then addressing, how to address the memory, how to store the data into the memory, all these concepts. Now we will be continuing the same thing. We'll start with the basic input output operations, basic I/O. As we all know that input and output devices which are connected to the processor has to be accessed, means data has to be transferred in between. Data on which the instructions operate are not necessarily already stored in the memory. Data needs to be transferred between the processor and the outside world. That is, let us consider you have a keyboard and you have an output device display on it which has been connected over. I need to transfer the data between the input and output devices. I/O operations are essential. The way they are performed can have a significant effect on the performance of the computer. How effectively, how long that you will take to transfer the data between I/O devices and the processor. There are program controlled I/O. In the program controlled I/O, you consider an example of reading a character input from a keyboard, and I need to produce that character output on a display screen. Suppose if I say from keyboard I have typed a letter A, which has to be displayed on the display unit or display device as letter A. So how the rate of data transfer, these are the things which you need to remember while accessing the I/O device. One is rate of data transfer, and the difference in speed between the processor and I/O devices will be operating at different speeds. You need to provide a mechanism to synchronize the data transfer. So in order to synchronize the data transfer between the I/O device and the processor, there is a solution. So on output, the processor sends first a character, then wait for a signal from the display unit that the character has been received. So it will, as this is as there is a mismatch between the speed. So how this will be addressed means by providing a waiting signal. So processor first it sends the character to the display unit, and then it waits from the display unit that the character has been received from the processor. While sending the input signal, first it sends the then it sends the second character. So input is sent from the keyboard in the similar way, same manner it proceeds. Suppose let us consider this structure. You have a processor and you have an input device. This is your input device and this is your output device as a display unit. There is a flag bits, so we call it this as a waiting bits or flag bits, and these are the registers which are meant for storing the data. So first what it will do, processor, suppose if it has to receive data by the display unit, so first processor will send the data to the display unit that will be stored in data out register. Then the processor keeps on waits from a display unit status whether the data has been received correctly or not. That means if it is received, then in turn then it sends the second character. Similarly, from the input device, suppose if the data in register is filled with the data to be transmitted, S in flag bit will be enabled, indicating the keyboard is ready to transmit the data from input device from the keyboard to the processor. So once if the data is transmitted, the data in register will become free, then the procedure continues. So you will have registers, flag bits and device interfaces. So these are the registers, these are the flag bits and these are the device interfacing units. So you will have in between an interfacing unit, IMU. So the machine instruction that can check the status of the status flags, that is SIN, SOUT, then transfers the data. Suppose read wait and write wait while transmitting the data to the output device and while receiving the data from the input device. So it will branch to read wait location. If SN bit is equal to 0, it keeps on waits. If SN bit is equal to 0, indicating input device is not ready to send the data. That means data in register is not filled with. So once if SN bit is equal to 1, indicating the data in register is filled, now it is ready to, the input device is ready to transmit the data. So input from data in register will be copied to the processor register R1. So write wait loop, if I say, that is accessing between the processor and output device. So in the output device, it will keep on wait if SOUT bit is 0. That means the device is not ready to receive the data. If SOUT bit is equal to 0, the device is not ready to receive the data. Suppose if SOUT bit is equal to 1, indicating the output device is ready to receive the data. That is, then from the processor, the data will be transferred to the output device. So here what is happening, as the speed of IO devices and the processor is different, in order to synchronize the speeds, we will be checking the flag bits. In this case, we will be keep on waiting till the flag bits were ready. Meanwhile, the processor keeps on waits. Processor time will go as a waste. So instead, we can have a separate different technique without waiting for the input on output device becomes ready. Processor can keep on does its work. Once if that device itself, if it is ready, that device itself will send a signal saying that I am ready to send the character or I am ready to receive the character. Then the processor will send, in turn the processor will send a signal data to transmit. There are two types of IO devices, memory mapped IO and IO mapped IO. Major difference between memory mapped IO and IO mapped IO is, in memory mapped IO you have a different address for memory and different address for IO devices. Memory mapped IO, different address for memory and different address for IO. That means in the same suppose let us consider I have 1000 as the address of memory. 1000 can also be an address of IO device. Same address can also be used because you have two different memories, one for IO device separately and memory device separately. Whereas in IO mapped IO, for memory and IO, for both you will have a same address. In the memory itself, there is a segment allocated for IO devices for accessing. So same address can be used for memory as well as IO in case of IO mapped IO. So memory mapped IO, some memory address values are used to refer to the peripheral devices and buffer register. There are no special instructions needed. All the instructions whatever we make use for memory transfer, that is load and store, same instructions can be made use in case of memory mapped IO. Whereas in case of IO mapped IO, you need special instructions like in, out instructions. So coming to this, suppose let us consider move data in R1, that means from processor data has to be transmitted to data in register, or from register data has to be transmitted to data out register. Then it will go first to read wait and write wait loops. In the read wait loop, it will check the bit number 3 in status register, so which is nothing but SIN flag bit. If that bit is equal to 0, then again it goes back to read wait till that becomes 1. It will be in the same loop. If that becomes 1, then it will transmit the data. Similarly, the write loop. Suppose if in the initial state, if SIN is equal to 0 and the initial state if SOUT is equal to 1, is there any drawback of this mechanisms? You observe you have two wait loops in this case. Two wait loops we have. One is read wait loop and write wait loop. Processor execution time is wasted in this case. Processor has to keep on wait till the device becomes ready. Alternate for this problem is using an interrupt, that we will discuss in the next session. So coming to next topic, which is a stack. Stack is nothing but a list of data elements, or usually it could be a words with accessing restriction, that elements can be added or removed at one end only, not at both the ends. At one end only you can add the element or you can delete the element. So the end of that is, we call it as a top of the stack, TOS. The other end we call it as a bottom. Usually it is working in the principle of push down stack, not push up, push down stack. So it works on the principle called as last in, first out. Last data whatever you have loaded, that will be fetched first. Basically in stack you will make use two instructions. One is push, another one is pop. One is push, is to push the data from registers to the memory location. Pop is to read the data from pop is to retrieve the data or fetch the data from memory location to the register. So in order to write or read the data, you need a address of that memory stack. So the address of that top of the, as we know that we have one end fixed, another end which will be where you will be adding the data one upon the other. So top of the stack will be holding, the address of the top of the stack will be holding in a one register. We call it as a stack pointer. Stack pointer always holds the top of the stack address, keeps track of the address of element of the stack which is at the top end at any given time. You can observe it works on the last in, first out principle. This stack bottom, which is fixed, one upon the other data will be loaded over here. Stack pointer holding the address of the stack. This is current stack, top of the stack. So while storing the data, it will be decremented by 1. See, from 6 it will become 5, then copies the content. While retrieving, first it copies the content and then increments by 1 using push and pop instructions. That's what here it is. Push instruction means first it will be decremented by 1, stack pointer is decremented by 1, and then data register will be, then content in data register will be copied to the memory. So first decrement and copying, pushes. Then pop is copying and incrementing. First it copies the content, then it increments by 1, because it is a last in first out principle and it grows in decreasing order. While loading the data, it grows in memory will be growing in decreasing order. So push instruction and pop instruction. Push is decremented by 1, stack pointer is decremented by 1, and then data register is copied. First in pop instruction, data register is copied, then stack pointer is incremented by 1. As I already told you, in the memory you have different segments: data area, program area, stack area, like that. If it is a program area, the address is held in program counter. If it is a stack area, the address is held in stack pointer. If it is a data area, it will be specified in the registers, address registers. Queue, which is working based on the principle of FIFO, first in first out. It is again storing the data in memory, but it grows in the direction of increasing addresses in the memory, not in decreasing addresses. Increasing addresses, new data will be added at the back. So you have two ends. One end, from one end it will be retrieved. Two pointers you need. At one end you will be loading the data, at other end you will be retrieving the data. Major difference, if you observe, queue works based on FIFO, stack works based on LIFO. One end is added the item, other end will be removing. So here one end is fixed. Using push and pop you will be adding and deleting, removing the data. So whereas here two pointers you need, as you have one end to add and another end to remove. Here we have only one pointer. You don't have any fixed size. Here you can fix the size of the stack. Next we have a subroutine. Suppose in any given program it is necessary to perform some particular operation for many number of times with the different data values. So in such cases, writing a block of instructions which is executed in the same task for n number of times, we can write that as a subroutine. So however, to save the space, one copy of this block is placed in memory, and any program, if it requires that, will be used using a subroutine by simply branching it to its starting location. So when a program is branched to a subroutine, we say that calling the subroutine, we are calling a subroutine. So that can be done by using a call instruction. After the subroutine has been executed, the calling program must resume the execution. So continuing immediately after the execution, after the instruction that is called the subroutine. So we say that the subroutine is said to be returned to the main program. So we call that is by using an instruction called as a return instruction. So we have a calling program and called program. Using a call instruction, we'll be calling the program subroutine, and using a return instruction, we'll be getting back to the main program. So whenever you call a subroutine, while means program counter will be holding the address of the program area. So present instruction address, suppose if it is stored in a program counter, next instruction address, whenever you call a subroutine, it will be routed to another location. Again it has to return back to the main program now. So the return address has to be saved. So PC must be saved by the call instruction. Why we need to save means, in order to enable for correct return to the calling program. So it is actually a linkage method. So you will make use a link register over here. Program counter content will be copied to a link register, a special register which is used to store the subroutine return address of the main program. So call instruction is just a special branch instruction which performs the following operations. Majorly it stores the content of PC to the link register. Reason, I need to know the return address. So PC content has to be saved, and then branch to the target address specified by the call instruction. Then return instruction you have, which is a special branch instruction that performs the operation as it branches to the address contained in the link register. It will be returned back to the main program. This is an example. Suppose let us consider, so this is a calling program and this is a subroutine. You are calling the subroutine at this location using a call instruction. This is a label of the subroutine. The address of the next instruction, usually PC is holding it. So first you need to store the return address. That means after completing this part, it has to return back to the main program. So this return address has to be saved. Return address will be saved in link register upon call instruction. 204 will be saved to link register now. Now PC has become free, so PC will be loaded with now the address of the subroutine. Subroutine address is 1000. That will be loaded into PC. So PC will be routed to this and it executes the instructions in the subroutine. Upon completing, you will find a return instruction. Return, what it will do? The link register whatever you have will be loaded with link register content will be loaded into PC. So PC will be having now 204, which is the address of this calling program. It executes the instruction from here. So upon call instruction, you have the following operations will means upon subroutine calling, these things will happen. First, it copies the contents of PC to link register. Then PC is copied with the subroutine address. Then executes the subroutine. Then upon return, what happens? Link register content will be copied to PC. Then main program is main program it will be returned. So parameter passing, all these things were not there in your syllabus. Then coming to additional instructions, you have additional instructions as logical shift operations, rotate operations, arithmetic shift operations. Under logical shift, you have two shift, left shift and right shift. Logical shifting and arithmetic shifting, major difference is in arithmetic shifting, the sign bit will not be means the sign of the data will not be lost, whereas in logical shift the sign of the data will be lost. So the vacated position will be filled with zeros in logical shift operation, whereas in arithmetic shift operation the vacated positions will be filled with the sign bit. Suppose if I consider logical left shift, so this is the data before performing the operation. So you are shifting towards left by 2 bits. So if I shift the data 2 bits 0 1, now first bit shifting will be copied to carry flag, next bit shifting 1 we have, which will be copied to here. The remaining bits is 1 1 0 and all these 0 1 1 will be moved. This is vacated position. The vacated positions are copied with zeros. Same thing happens with right shift. So coming to arithmetic shift, even here you have arithmetic right shift and left shift. So if it is a right shift, if I consider it is shifting towards right. So towards right means first bit upon first shift you will have a 0 will be copied over here. Next shift 1 will be copied over here, will be leaving with zeros, and these data will be moved, and this is vacated position. Vacated positions you observe it will be copied with the sign bit. Last bit is a sign bit, so this is copied over. So upon arithmetic shift we don't lose the content, whereas we don't lose the sign bit, whereas the logical shift operations we will be losing the sign of the number. The vacated positions will be filled with zeros. Coming to rotate operations. So here upon rotate operation the original data will not be lost. If I return want to return back, I can return it back the number. So this is with carry, without carry, left shift operation. Similarly right shift operation with carry and without carry, rotating the data towards right or left. Apart from that we have a multiplication and division. We don't have division instruction, multi instruction we have Ri and Rj, these two will be multiplied and copied over. Only one half, another half means if I multiply 16 bit with 16 bit you will get 32 bit data. So register can store 16 bit data, lower half of the result will be stored, upper half of the result will be eliminated. Even here the same, only reminder may be placed in Rj plus 1, quotient will be placed in Rj. Apart from this, these are the logical operations that you have, and operation or operation. This encoding is not there. We'll see the next part in next session, which is the part B, input output organization, IO organization. So thank you.